Yeah, we're going to have to sweep one of these over. So let me tell you what we're going to do today. So what we're going to do is to take the problem number 2 from the homework and use it as a didactic example and work through it. And I want to show you my philosophy. Do we have some extra copies here? I know I made enough. Yeah, so what I want to do today is take problem 2 from the homework and work through it as an example and really take my approach on this. And I think by now everyone's pretty much sort of on the ball. I mean, these are problems that are dealing with structure solution of an unknown, and that's sort of half of what you get. You get some wacky product, but usually you kind of have an idea of where things are, and so you're working from some reaction. You know what you put in there. You're not a natural products chemist, and so you're usually having a starting point, and that's why I also think the analysis part is really, really important. But if you absolutely don't have an idea, obviously the most important information is like molecular formula and getting degrees of unsaturation. I've started us in the course with IR because I think it's really, really important to get the functional groups in the molecule. And obviously it can be mass spec and so forth for a molecular formula. I want us all on the same page on NMR where you go through and you'll letter the peaks. It's just a way we can all communicate. And the other thing is read your spectrum when you're working on NMR, and I'll show you what I mean today. Really, really jot down your thoughts and so forth. Carbon, we're numbering the peaks. And again, you're going to be getting information. You're going to be thinking about symmetry when you're doing this. You're going to be thinking about peak positions. Usually, if it's available, I'll go through the depth, assign your quats, etc. next. So I'll say basically to quats, CH, CH2, CH3. Usually next, I go to the HMQC. We've already seen lots of situations where you have diastereotopic protons and you're trying to put the framework of the molecule together. And so the COSY is actually more useful once you've figured out diastereotopic methylenes and so forth. COSY is going to build up fragments. And it's really, really useful to be keeping a scorecard as you go along of sort of what do we know, what don't we know, what are our fragments, what are our interesting functional groups. HMBC is super useful for putting the pieces together. And you get a ton of information from HMBC, so it's really useful to work strategically around isolated things. Isolated methyls are a gem. Quats and carbonyls can be a real gem for this. And finally, I like to go ahead and use the NOESY or NOE to address issues of stereochemistry. Obviously, you're also going to use coupling constants when appropriate. So I'll say also J values. So that's sort of a general philosophy on structure solving. And I thought problem number 2 is a useful example of this. And I've handed out key parts of problem number 2. I've also handed out the low-level analysis that's pretty mechanical, so we don't spend a lot of time on it. So when I looked at this, let's see, I got C15, H18, O3. And I always look and just say, OK, if it were C15 with oxygens and so forth, what would it be? It would be 32 hydrogens, 32 minus 18. That gives me divide by 2, as that's the degrees of unsaturation. So we get 7 degrees of unsaturation. The IR on this one is really, really interesting. So the IR has a peak at 1783, and that sort of sends up a red flag. It's, we don't have like an acid chloride in there. We're going to see you don't have any of these paired types of things where it's consistent with an anhydride, say. And so that starts to look like some sort of strained ring. When we look at the C13 NMR, you're going to see there's nothing that's consistent with a ketone, with a sort of normal ketone in there. So, I'm thinking that's pretty typical for like a gamma lactone. We see 1660, 1629 in the spectrum. Conjugation can shift things to lower wavelengths. So that's kind of where I'm starting out in looking at the data here. And now I want us to focus on reading the NMR spectrum. And I've given you, as I said, two handouts, one that you can work along with me, but one where I've also done a lot of the low-level analysis. And you should all, from this week's homework, be on the same.
And will we get the mass spec on the final?
You may. It depends. So I guess my philosophy on this one was I didn't want anyone to get wildly off base on this one in terms of molecular formula. I wanted people sort of on that wavelength. So this spectrum was interesting. So you went through, and everything's resolved to one hydrogen multiplets and a couple of 3 hydrogen peaks. There were some things that I thought were really, really interesting on this. So, you can kind of see this in the heights of the methyls here, right? This is a methyl singlet. Here we have a methyl doublet. So already you're thinking, CH3, CH2, CH3CH for this. This is like an isolated methyl, right? These are peaks. If you've lettered all the way across, right? This is K, this is L, right? We just went A, B, C, etc., D, E, F, G, H, I, J. So we should all, the other thing that was really interesting about this, so you'll look at this position here. It's the 3 hydrogens, it's a methyl. Now, and it's a methyl at an interesting position because you're going to have something shifting you down to about 2. That's your allylic, benzylic, alpha to a carbonyl position. The other thing is if you look at it, you can see it on the peak printout. You can see it reflected in the heights that it's shorter than the other methyl singlet. So this guy's a doublet, and I think our J was, what, 1.2 hertz or 1.1 hertz, somewhere around there. This is classic allylic or homoallylic type of coupling. So we know something's going on with this methyl group. If you look, there's one other, well, there are a couple of other interesting features on this spectrum. So peak number C is interesting, letter C. C is interesting for a number of reasons. His position is very interesting. We'll see in just a moment that he's not from the HMQC. He's not associated with a double bond, right? We have 2 alkene protons. In fact, these guys are kind of interesting because they're both doublets. J is equal to 9.9 hertz. So immediately you're starting to think maybe a cis alkene, right? Cis is about 10 hertz typically. Trans is about 17 hertz. So I'll put, and I'm sort of jotting down ideas and thinking, kind of putting down question marks here as I'm going along. This guy's interesting because he's a doublet, but there's a little something more going on with him. And so here's the expansion of C. I didn't give you a handout on that. You've got it on your main problem. If you look initially, you might think that this is a doublet of doublets, and that might be how you call it, or call it an apparent doublet of doublets. But you notice there's really a little something funny going on here. It's what we're actually going to see that it's a doublet of quartets. The outer wings just aren't resolved. Again, the J is about 1.2 or 1.1 hertz, and that's just barely at the resolution that you're going to see splitting, because your line widths are typically about a hertz, which means you just barely have things resolve out. I guess the other thing that's interesting is down in this region, right in the aliphatic region between the allylic, or around the allylic methyl. So we wouldn't necessarily know this in terms of what's happening at this point, but we're going to see it later. So this is really interesting. We've got these multiplets here. They're very nicely resolved, at least for these three here. So you can see that you have a doublet of quartets, or quartet of doublets rather, and another quartet of doublets, and a triplet of doublets. You can see this from the heights of the peaks, that you're getting basically this 1, 3, 3, 1 type of pattern with some tenting inwards. You can see some coupling partners. So you're dealing with a situation where you've got 3 big J values in one of them, 2 big J values in another of them, and then you've got a smaller J. This is like the types of things we've seen in the past with geminal couplings and axial couplings. So that's sort of an interesting read. These guys have just 1 big J and then a bunch of little couplings. That's our allylic methyl. Anyone recognize this pattern here? Yeah, doublet of quartets. You notice the 1, 3, 3, and then of course your 1 is sort of hiding under here, but you see that in the heights, and then another 1, 3, 3, and your 1 is hiding under there. So again, that's just sort of a neat thing as to what's happening. In terms of actually understanding it, well, as we start to get into the structure and the COSY, we'll be able to understand this a lot better. But this is what I like to do initially, is just come up with a read on things. You know, I went through the carbon and numbered it, and you're basically numbering 1 to 15. That's all written out there for you, so don't bother to try to follow along here. 8, 9, 10, 11, 12, 13, 14, and 15. You can almost get your quats by inspection. They're usually low. Remember, quats have much slower relaxation times, so with normal relaxation delays, your magnetization isn't returning to the z-axis. You also don't have hydrogens on them, so you're not getting a nuclear overhauser effect here. Number 9 and number 10 are interesting. They're 0.4 parts per million apart in the C13 NMR. That's right at the limits of where one can practically start to use HMBC to figure out what's lining up with what. You can, but you have to be really careful, do expansions, increase your number of points in the virtual domain, in the F1 domain to 1024, and work pretty hard. We're actually not going to need this. We'll see later on in a moment when we come to the HMBC. We'll actually be able to figure it out because 9 and 10 are very, very distinct. I went through, and again, this is all on your sort of quick and dirty 4-page handout. I went through and basically on that handout assigned your C1, C2, C4, C5, and C9 ended up being quats. This particular one was done with a depth 45. The depth 45 was the one we talked about at the end, where you have that theta Y pulse of 45 degrees that gives you your methynes, methylenes, and methyls. Not done too much. You can see pretty much you can pick out your methynes and you can pick out your methylenes. So 11 and 13 are methylenes. 12, 14, and 15 are the methyls, and then you have some methynes in there. All right. And again, this is sort of the low level analysis on it. I just went through my my HMQC and correlate. And this is going to be, this last page of that second handout really is going to be our Rosetta Stone for taking it from here. So I went through and did the low-level analysis and lined things up. And again, if you're having any trouble visually, just get out a grid, or if you're working on a computer or on an iPad using Acrobat, you can use Command U and it'll slap a grid, but it's very easy to trace over and trace up. All right, so that takes us through our preliminary analysis. And let's see, if I want to, let's go to the COSY next, and I think here's where I'll start our real analysis on this. All right. So I have a couple of expansions that are useful. We could muck around entirely on this spectrum, but I'll just start. I'll get this guy out of the way. So we've got our alkene region here. There's two doublets with J of 9.9 hertz are crossing with each other. So we have 3A and 6B, and 3A and 6B. And of course, our diagonal runs right through the COSY like so. And so we've got our 3A cross 6B. So I'm pretty sure at this point that we're talking about an alkene that's coupled together. I guess let me put down maybe a sort of a summary from the HMQC. So C1 is a quat, C2 is a quat, C3, HA, C4, C5, these are quats, C6, HB. This is all just from our HMQC analysis. C7, HC. And I guess the thing that was sort of interesting, I try to keep a note of what's interesting. This is at 81 ppm for the carbon and 4.8 ppm. So that's probably connected to an oxygen. I think you probably can be pretty confident that that's connected to an oxygen. Let's see, we have C8, HH, C9 is a quat, C10, HD, C11 is HG and HJ, C12, H3K, so that's one of the methyls there. C13, HF, HI, C14, H3L, and C15, H3E. So that's the one that's at 2.1 ppm, the one that I think is in some way allylic, because it can't be, if it's alpha to a carbonyl, it's just going to be an isolated methyl, right? It's going to be a methyl ketone. So it can't be a methyl ketone and be a doublet. If you've ever seen, the only case you could have something that looked like a doublet would be if you had split field, if your shimming was off on the instrument, and then all of your peaks would be split into two peaks, and you'd see it. Your TMS would be split, your chloroform, anything that looked like a methyl singlet. In general, that'll occur if you have too little sample in your tube, or if you have something wrong with the shimming on the spectrometer. Okay, so at this point, I'm really ready for some more serious analysis. And I want to build up the structure at this point and get as many fragments as I can. So we have C3HA, and we're pretty sure, maybe I'll put a dotted line just to indicate that we can't be absolutely confident there's a double bond. You could conceivably have a double bond connected to another double bond. All right, let's see. We have a bunch of unknowns. If that's the case, we've got, let's see, our C1 has got to be a carbonyl. Our C2 has got to be a carbonyl. C4, and again, I'm pretty sure we're talking about that then being double bonded. We're not going to be able to do anything with C15, H3E. Actually, well, we'll come back to these on the scorecard. C12, H3K, C9. These are going to sort of be problem children. So let's work through the expansion of the COSY at this point. All right, so very, very mechanically, I go through and I would go and label my peaks C, D, E, F, G, H, I, J, K, L, and then just put the numbers here, 7, 10D, 15E, and let's see, 13F, and 11G. It's nice to have one of these 0.5 millimeter pencils because they really help you work in crowded spaces. Let's see, 12K and 14L. And let's see, so that's 15E up there. So let me just go ahead and we'll do 7C, 10D, 15E, 13F, 11G, 8H, 13I, 11J, 12K, and 14L. All right, so we've got our COSY here. So 7 is interesting. So we've got our diagonal. Probably a good idea to get in the habit of just drawing a line on it so you can have it as a point of reference. I'm a big fan of keeping my spectra square. I try to, particularly with proton techniques, I guess, to really keep my spectra square. It helps me get better control. I like on the instrument to enter my values through the keyboard rather than just grabbing it with the cursor. Okay, so we've got some interesting stuff going on here. So we've got 7C cross 15E. So that's kind of interesting. Remember, that was the pair. That's the allylic methyl. And we know that that's allylic coupling. Because if you have a methyl directly next to a CH, your J value is going to be close to 7 hertz. And 7, if there are a couple of electronegative atoms, it might be 6 or 5. But it's not going to be 1 hertz. And we noticed that 7C was also split into this doublet of quartets, or what at least looked like a doublet of doublets. So the other one that's interesting, so we don't yet know how 15E is connecting in here. The other one that's really interesting is we get 7C to 8H. And that's kind of nice because that's giving us some connectivity at this point. So if we start to now, we can build up build up a framework for the molecule, assuming I can find my marker. All right, well, we'll take the backup marker. So, okay, so we've got C8HH over here, and we've got C7HC over here. Somehow, and we don't really know, we probably have an oxygen on here. Somehow, that C15HE is tying into this, and we really don't know exactly what's going on right now. All right, we can continue to build up our framework here. And so we get 8H to 10D, and we get 8H to, and let's see, we get 14L to 10D. And so if we look at that and continue to build up our framework, so, oh, I'm sorry, we get 14, what am I doing here? 14L to 10D, right, yeah. So we get C10 HD and C14 H3L. And so at this point, we sort of want to keep track of our valencies, right? Our valence is full on this methyl group. We have a valence here. We have a valence here. We have a valence here. We have a valence on the oxygen. And we're going to continue to build up our framework. So we move into this crowded region. I just did it on this expansion here. You could easily go to another expansion. So we get some interesting ones. We get 13F cross 11J. We get 13F crosses 13I, so a geminal. So that's not particularly useful. And it looks like, and we see the corroboratory one over here, it looks like we get 13F crosses 8H. And so that's interesting, because now that allows us to continue to build up our chain. And so at this point, we're building out to C13 HF HI. So it's kind of like solving a puzzle here. We have a valence over there. And now we just continue across here. We get G cross I and G cross J over here. So let's see, 11G cross 11J, that's trivial because that's just a geminal coupling for that upper one. And then we get another one, which is 11G cross, let's see, cross 13I. Okay, so that basically gives us, and so that's G and J. And so that basically completes this fragment. Everything else we're going to see here is going to be redundant. So you've got this off-diagonal peak here of H cross I. 8H crosses 13I. And so that just reinforces the information we have over here. And then we have our last cross peak is J cross I. So 11J crosses 11 crosses 13I, if I'm seeing correctly. All right, so that basically takes us as far as we can go based on the connectivity, and we still have that allylic methyl. All right, this is where we want, so this is, after this point is where we really have this scorecard up here of these are our problem children. This is sort of where we don't know what to put in yet, and it's where we want to focus. Now, invariably, it ends up being quants and isolated peaks that are the ones that are the problems, but they're also the ones that are tremendously beneficial in the HMBC. And the reason they're tremendously beneficial is this problem of having your isolated peaks, of having 2 and 3 bond CH coupling both show up, and show up not guaranteed to show up in the HMQC, in the HMBC, means that you really want to be looking toward isolated peaks to help serve as linchpins. Let me show you how this works here. So here's our HMBC. You can pretty much go ahead and cross out all your J-coupled peaks, the HMQC type cross peaks, the ones I sometimes jokingly refer to as vampire bites. So I think, let's see, I think I got them all. There's one more hanging out down here. And let's see, one more for C over there. All right, I want to be good about this. So again, I'm going to very slavishly transcribe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 for my carbon axis. And if I just do my letters, 3A, 6B, 7C, 10D, 15E, let's see, 13F. This marker is getting a little dull. Let me get a sharper one. All right. 11G, 8H. And by now these guys should be becoming good friends, or at least worthy adversaries. 13I, 11J, and 12K, and 14L. All right. So the isolated peaks are the ones that I generally start with. You don't have to analyze absolutely everything. It's helpful in the end maybe, but initially I'm going through and sort of looking, okay, we've got 1 to 3A, maybe, and this is a little confusing, 1 to 6B. Remember, small, I'll put a question mark there, small couplings can end up being confusing here. And then 1 to 15E. Now, this last one is really a, let's see, I guess, all right. So at this point, I guess I'm trying to figure out what's going on with the C1 carbonyl. And so this one is interesting. So we have this methyl, this allylic methyl, and that's really useful. We know that methyl isn't directly connected to C1. Right, we know it's allylic, we're seeing allylic coupling, we don't have a methyl ketone in there. And yet it's isolated. That's telling us something. That's telling us that as we build up this structure, we can now stick our C15 H3E off here. So that's useful. We know it's got to be on a double bond carbon. We've got these two guys here, the 1 to 3A and 1 to 6B, and we were pretty sure we had a cis-alkene in there. And so that's going to help us out over here because now, remember, those have hydrogens on it. You can't have HA on the same carbon as a methyl. You can't have HB on the same carbon as a methyl because you'd see a coupling of about 7 Hertz. All we're seeing is this very low coupling. So we've got this guy over here, and these guys have hydrogens. When I'm not certain, what I like to do is do something like this. I don't know if it's carbon 3 or carbon 6 connected to carbon 1. I could probably look it up in Pretch and see which has a bigger coupling constant, because one of these, if it is really coupling, is very small, and the other is pretty big. And 2 and 3 bond couplings can be surprising. But if I go C3, C6, HA, HB, later on I can make certain with it. And similarly here, I don't know if I have C3 or if I have C4 or C5 over there, but I have that. All right, let's continue here. So I want to move on to carbon number 2. Carbon number 2 is another carbonyl. And carbon number 2 is really interesting. We get 2 nice peaks here, 2 to 10D and 2 to 14L. And that 2 to 14L is another real gem because you've got this methyl over here. And this methyl is isolated here by 10. So I know that carbonyl, in order to get that cross peak with 14, that carbonyl C2 has to be over here. And we have 1 valence on it. Now, we can find out later by the process of elimination. I wish we were seeing a cross peak between HC and carbon 2. That's going to depend on the dihedral angle. But we've used up 1 carbon with a ketone here. That explains our 1660. It's a conjugated carbonyl. We have a lactone. We can close this, or we can wait till later on for process of elimination here. Let's continue our buildup. There's nothing too much else that's going to come useful off of our alkenes. I'll go through. We've got a little bit of useful stuff. We've got 3 to 11J for this one, and we've got 3 to 12K. I think I'll grab my sharper pen. 3 to 11J and 3 to 12K. And so far, not quite sure what to do with that. It's going to be useful because we're trying to connect. We've got this fragment here, and I'm sort of struggling at this point how to put them together. And let me show you. These we could go ahead and put them in a moment, but I'll show you where things come in very, very nicely in just a moment. 12K is interesting. 12K, see, this is starting. This one, that's very interesting because we have an isolated methyl here. And so we've got this problem here. We're taking care of this guy, we've taken care of this guy, we've taken care of this guy, we've taken care of this guy. We have 2 carbons left. And we know that isolated methyl is not directly coupled over here. And what's very nice about that is it really leaves you with a process of elimination. But let me show you how beautiful this works. So here's your C12H3K. But let me show you how beautifully this works. So let me switch tracks at this point. And I want to go directly off of that isolated methyl. So that isolated methyl ends up being a lovely, lovely linchpin. You go and you see it's 4 to 12K. We go ahead, we get, let's see, we get, okay, then we have an interesting one here. So we have 11 to 12K is up here, is up there. And then we have this cross peak. Now, as I said, 9 and 10 are really, really close to each other. You might be able to expand in and get this resolved. Maybe not. Depends how good your spectra are. If I were running this in the lab, I might go down and do some additional expansions. But what's really nice at this point is you know that 10 is taken out of commission. 10 is now completely isolated over here. And so this 12K ends up being this fantastic linchpin that's putting together the molecule, because 12K is crossing with 3. And so that helps us assign that 3 has to be this one. So that resolves that, which means 6 is this one. So 6A and B are this one. It's crossing with 4. So that linchpin puts in our connectivity here. At this point, we have 2 valencies that are left to be filled. And it really isn't very hard because we have 2 valencies left on this part of the molecule. So in other words, now we're also crossing with 11. And so that puts in this here. And that puts in that there for our connectivity. And so we can go through and check on some other aspects of connectivity, but I think at this point we can go, for example, we see some duplicate information off of 7, and so for example, by a similar logic, you see 9 to 7C, although there's some ambiguity. We've got some cross peaks over here, like 5 to 15E, that are giving us information we now have. But what I want to do right now is to move into this final stage of determining the stereochemistry of the molecule. All right, first thing I'm going to do is redraw. And I'll redraw it to give us our connectivity, and then we're going to look at our NOEs. All right. So C13HFHI is on the top. And C8, I'm just drawing it in a particular way, C8HH and C11HG, and C9 and C4 to C5, C1 carbonyl, C6 HB, C3 HA, C12, H3K, C15, H3E, and we continue to C7, HC. We have a bond here, C10, HD, C14, H3L, C2, carbonyl, and the oxygen of our lactone. All right. Now, in terms of where where I go with something like this, generally in terms of figuring out stereochemistry, I'm just going to go ahead and start by drawing a cyclohexane ring. That's probably the one thing I can do kind of sort of clearly. And the great thing is you can take a stab at stereochemistry. And very quickly, of course, you're not going to get absolute stereochemistry, but very quickly you'll see if you have your relative stereochemistry right. So let's just take a stab. So here's that whole unsaturated ring over here. All right, and let's take a stab. I'll put in an angular methyl, an axial methyl, that's C12H3K. And let me just start. The one thing I can do is draw chairs. And once you're dealing with a 5-membered ring, you sort of fake it. And so you can draw a lactone here. And we have a substituent here and a substituent here. And what I would probably do is start with this guy over here and see how things work out. And so we've got, let's see, we've got 7 over here. We've got 8 over here. We've got 10 over here. All right, so let's see how things work out on the NOEs. All right, so this NOE, the bottom NOE, is a very, very nice experiment. The bottom NOE, we've got this clear shot at 7C, and he really, really answers things for us. So you irradiate 7C, and you look, and there's this lovely enhancement of 10D. You've got a subtraction artifact on your allylic methyl. That's pretty normal. You see a clear enhancement of 13I. It looks like 8H has some J coupling to it, and maybe maybe a tiny bit of enhancement, but also something going on with J coupling because it's not the same multiplicity. And we've got 12K. Okay, so that's interesting because we've got our 7C here, and you irradiate him, and 12K lights up like a Christmas tree. 1,3 axial interactions are very nice for getting NOEs. On my handout, that was the one I showed. It was just like 2-point-something angstroms. Let's see. We have 10D over here. So that's interesting because that is really giving us the rest of our stereochemistry in the molecule. That's giving us, we need this one center over here, but we pretty much have everything that we need. We really can't have a translinkage here. And then let's see, we have on the back, I guess that's, what is that? That's HI is over here. So I'll try to draw it up here. So we get that NOE to HI. That's very nice. We look at our other experiments, and this one's kind of complementary. You irradiate 10D, and it looks like we have J coupling to HC. So I'll write coupling. You notice that antiphase thing. Looks like we get a little 1 to 13I, a little hard to tell what's going on here, subtraction artifact, and we get 7C. So in other words, we irradiate HD, we get 7C. So that's good. That's kind of up, up. Now, the last thing here, all right, this one's kind of a mess because we're coming in, we'll see on the next page. And so I'm trying to hit at this point 14L, and you'll see on the next page what's going on. So we've got our C14H3L methyl, And on the next page, I zoomed it a little bit. And so this is the same experiment. And you can see, remember how I said it's tough to hit peaks that are close to each other? So we're hitting here, we're hitting 14L, but we have a little bit of incomplete selectivity. So we're hitting 12K just a little bit. And so you can see, mostly we're hitting 14L here. And you're getting this very, very nice NOE to 10D. OK, that sort of makes sense. We're irradiating this methyl group. We're getting an NOE over to here. That makes sense. They're close to each other. It looks like we're also getting an NOE over here to 13F and to 8H. So, OK, so 8H, remember I sort of was wondering about the stereochemistry of this. So 8H is on going down. And let's see, this is 13 on the back here. And so 13F is equatorial. So we get that nice NOE over there. And so that kind of finishes up our stereochemistry on our molecule. And so just good idea. Snap it with a camera.
Because I can't draw with crap.
So that is a good idea, though. So just to sum up, what we basically did was, after going through this mechanical part of labeling our resonances, was really try to put together fragments as completely as possible, look at those isolated peaks, and try to use those as linchpins to tie the thing together. Keep our wits about us about chemical shifts and our observations of things like allylic coupling, and then use NOEs and J values. We didn't even go through our big J's and little j's, but you'll see they all fit into this axial-axial coupling, axial-equatorial geminal coupling model. So anyway, that's the general gist for sort of hardcore structure solving on medium-sized molecules.